Hi guys, this video is about Year 10 Numeracy Section 3A Irrational Numbers including surds. Before we start, I just want to say, please feel free to pause the video or replay the video as many times as you want. So sometimes you would rather stop the video and understand the concepts before moving on. All right, without further ado, let's have a look at the learning intentions. First, to know the meaning of the term rational number, irrational number, and surd. Second, to know how to identify a number as rational or irrational. Third, to know simple rules related to surds. And the last one, to be able to simplify surds using the highest square number factor. All right, let's have a look at some definition of real numbers. All real numbers can be located as a point on a number line. The real number system consists of different categories of numbers. There are natural, whole, integers, rational, and irrational numbers. And if you're going to do specialist math in the future, you're going to know there's another kind of number called complex number, which is not real number. I mean, which is it's a broader context of real numbers. Real number is part of complex number, but don't worry about that. Natural numbers are the counting numbers. Okay, so if you count the numbers 1, 2, 3, 4, 5, 6, 7, and 8, and so on, those are called natural numbers. And you have whole numbers. So on top of those counting numbers, you've got this 0. Okay, so and integers are all of the natural numbers. They're negatives and zeros. So you've got those parts for whole numbers, and you've still got negative parts. Okay, and they are all whole numbers. So positive whole numbers, negative whole numbers, and 0. Rational numbers. Numbers that can be expressed as a fraction, a over b. So there are 3 kinds of rational numbers. The first set includes the integers, for example, 3. So those numbers are rational numbers. The second type is like terminating decimals. So terminating decimals means this decimal number is going to be terminated, okay, which is in a contrast to the repeating decimals which we have here. So for example, 0.33333 and so on. It could go forever if you want. And this is actually essentially 1/3, okay? If you put that if you put, fraction line plays a row of decimal of division. So 1/3 is like 1 divided by 3. So if you calculate 1 divided by 3, you are going to get 0.3333, okay? 3 recurring. All right. And you've got irrational numbers, which are the numbers that cannot be expressed as a fraction. For example, pi. We know pi is roughly 3.14, but you could go for more, like 1, 9, 2, 6, and so on. The more you go, the more, it's just never terminating, okay? And it's not recurring as well. So it's neither terminating nor recurring. So these kind of number are irrational number. And square root of 2 is approximately 1.414. And you could go for more decimal places if you want. In decimal 4, there are the numbers that go on forever without a repeating pattern. If a whole number is not a perfect square, then its square root is an irrational number. Okay, so perfect square, we know perfect square numbers would be like 1, 4, and 9, 16, and so on. Okay, this is like 1 square, 2 square, 3 square, 4 square, and so on. All right. So if this whole number is like 25, it's a perfect square. And then if you take a square root, that's going to give you 5. Okay, so that's an integer. But if this number under the square root is not a perfect square, for example, 26 is not a perfect square, this is going to give you an irrational number, because it could not be simplified to at nice and simple integer like this one had before, okay? Irrational number. All right. Okay, here's a Venn diagram on the relationship between each set, okay? Natural number, you have the smallest set, natural number, and you've got whole number, which include 1, 0. And you could have integers, which is got negative part, like negative 1, negative 2, negative 3. Okay, apart from whole numbers, it's got negative numbers, negative integers. And the rational numbers, okay, apart from integers, you've got like a rational number like 0.34 that has a decimal, like a terminated decimal, or 1/3, which is approximately 1.33. Okay, and apart from rational numbers, you've got irrational number like square root of 2 or like pi. Okay, so if you put them on a number line, okay, on the same number line, like you have -1/2, that's a rational number, -3, that's an integer, so it's a rational number, and you've got √2 irrational number and pi irrational number. So you could have both rational and irrational numbers on the number line, and those numbers are called real numbers. Okay, because this is like this is another name for this number line is called real number line. Okay, because it's got all the real numbers in it. So basically, just in case you don't get confused, real numbers, in case you get confused, real numbers, it includes two parts, two big parts, rational and irrational. Okay. All right. When using Pythagoras theorem to find unknown lengths is right angle triangles, many answers expressed in exact form are surds. All right. The length of the hypotenuse in this triangle, for example, is √5, which is a surd. So this is a surd. A surd is a number that can only be expressed using a root sign. Okay. A surd is a number that can only be expressed using a root sign, sometimes called a radical sign. So this sign could be called root sign or radical sign. They are irrational numbers. Some examples of surds include √2, 5√11, -√200, 1 plus √5. All right. They can't be simplified anymore. They have to have root sign in it. Be careful, the following numbers look like the surd, but they can't be simplified to show they are indeed rational numbers. So √4 is actually 2. Cubic root of 125 is 5. And -4th root of 16. Okay. 4th root of 16 is actually -2 because this one, 2 times 2 times 2 times 2 is equal to 16. Okay, this all comes from your number sense. There's no specific way of doing that, because when you have 16, you just get a trial. You try, you get 16 sounds fair. You could use 2. 2 sounds fair. 2 times 2 times 2 times 2 is 16, is exactly 16. So 4th root of 16 is just 2. Okay, so -2. All right, the nth root of a number x is written nth root of x. Okay, so actually, when you have root, let's say √2, it could also be written as 2√2. Okay, so but this 2 in here, if you're just talking about square root, we usually just omit this 2, omit the 2. Okay, we omit the 2. If nth root of x is equal to y, then y to the power of n is equal to x. For example, 5th root of 32 is 2, since 2 to the power of 5 is equal to 32. Okay, which like we had the example before, 4th root of 16 is equal to 2, because since 2 to the power of 4 is equal to 16. Okay, 2 times 2 times 2 times 2 is 2 to the power of 4. All right, we've got some rules applied to surds, and these are the most important takeaway. Okay, you should be very, very familiar with those rules. First of all, √x² is going to be x. And root x squared is going to be x2. Okay, it's also going to be x. When x is greater than or equal to 0, x has to be greater than or equal to 0, because if x is less than 0, here, if you look at here, it's going to be square root of a negative number, which doesn't make sense to you, right? If x is let's say x is negative 5, you have square root of negative 5, which does not make sense to you. Okay, so x has to be greater than or equal to 0. All right, so let's have some example of these rules. Second, examples of the rule. The square root of x, let's say square root of 3 bracket square. So you have bracket square that's just going to give you 3, okay? Or 3 square root of 3 square that's going to give you 3 as well. Okay, remember that. This is an important property. Next one, square root of x times y is equal to root x times root y. So this product could be splitted. Okay, for example, square root of 3 times 4 is going to be square root of 3 times square root of 4. All right, and the last one, square root of x over y, is going to be root x over root y. So let's say root 3 over 4 is going to be root 3 over root 4. All right. Okay. So those ones, I've shown you some examples, and these rules should be in your mind. But this comes from practice. So you do some practice, you find easily to adopt those rules. When a factor of a number is a perfect square, we call that factor is a square factor. Example of perfect squares are 1, 4, 9, 16, 25, 36. Okay, 64, 81, 100. Just 1 square, 2 square, 4 square, 3 square, 4 square, so on. When simplifying surds, look for square factors of the number under the root sign and then use this one. I'm gonna show you example question later, and you understand this. Okay, don't worry about this just so far. Example 1, express each number as a decimal and decide if they are rational or irrational, then show this number on the same number line. Okay, first, this one, if you put root 5, root 5 is a surd, okay? It's gotta be rational, okay? And if you really want to look at what it is, it's about negative 2.236, okay? But of course, it's not finished. It's irrational. As a decimal, it's just it can't be finished. It's just approximately negative 2.236. Next one, B, negative 40%. Negative 40% just means per 100. So 40% is 40 per 100. So it's 40 over 100. And that's just negative 0.4. Okay. And last one, you put that in your calculator. Let me put it in. So this is approximately 0.286. All right, let's put them in this number line. Negative 2.236 is between negative 2 and negative 3. So it's somewhere here, negative 2.236. And negative 0.4 which is between negative 1, 0, and slightly to the right of negative 0.5. So this is your negative 0.4. And the last number, 0.286. Actually, I need to write this as negative root 5 to be precise. Okay, negative 0.286. It's about 1/3 of 0 to 1. So about here, 2 out of 7. Okay, let's give you a sense of how the numbers are related. Example 2, simplify the following. So remember the method we've suggested. You're going to identify what? Square factors. Okay, you're going to identify square factors. So negative 20, what I can do, this all comes from a number sense. Okay, I wouldn't say Yeah, it just comes from practice. There's no specific way, because when I see 20, I just look at what times what can make 20, and 4 times 5 can make 20. And luckily, fortunately, 4 is just a square number. So I can split this as square root of 4 times square root of 5. Remember that square root of x times y is equal to square root of x times square root of y. Okay, so we've got this perfect square factor. Square root of 4, that's just going to give us 2 at 2 root 5. All right, next one. 2 times root 300. 300 is like 3 times 100, okay? And 2 times, this is 2 root 300. So there's a multiplication sign here has been omitted. I have shown you. Times, so root 3 times root 100, okay? Split it. So 2 times root 3, and the root 100 is just 10, because 100 is the perfect square. So 20 root 3. 2 times 10 is 20. 20 times root 3. I don't need to show the multiplication sign. 20 root 3. Next one. 2 times root 27. 2 times root 27 would be times 3 times 9. Okay? Over 3. So 2 times, so we can split it, square root of 3 times square root of 9 over 3. So 2 times square root of 3 times 3, because the square root of 9 is 3 over 3. And luckily, we've got 3 here, 3 here. This could be simplified. Okay, so it's just 2 times root 3 over 1, which is just 2 root 3. All right, last example here. Square root of 125 over 16. All right, remember this. Square root of y over x, that's what we had before, is going to be square root of y over square root of x. So this could be written as square root of 125 over square root of 16. So square root of 125 is actually 5 times 25 over square root of 16. So actually, I don't have to show square root of 16 here, because we know square root of 16 is just 4, okay? I can just put 4 here to make it simpler. All right, I just need to focus on my numerator now, the top number, numerator. So square root of 5 times 25, that's square root of 5 times square root of 25. I apply this one again. So I apply this rule again, and over 4. So that's root 5 times 5 over 4. Okay. And usually we write the root, we write the surd to the end, okay? So 5 over 4 times root 5, okay, on the top. You could write to the right as well, 5 over 4 root 5. Both are correct, okay? All right, example 3, the last example I'm going to talk about. Express this surd as a square root of a positive integer. All right, so it's like a reverse procedure as we've done before. 3, I can make it as square root of 9, okay, because 3 squared is equal to 9, and 3 square root of 9 times square root of 2. So this is just going to be 9 times 2, square root of 18, okay. So we had square root of xy is equal to square root of x times square root of y, but reversely, you could go back to this, okay? So it's just it's a square root of a positive integer 18 now. The next one, 5 is going to be similarly, it's going to be the square root of 25 times square root of 3. And that's going to be square root of 25 times 3. And that's square root of 75. Awesome, we made it. All right, now it's your time to complete your exercise questions from 3A. And there are also some useful videos for you to have a look. Okay. All right. That's the end of the lesson.